through the fascinating world of numbers. By the end of this video, you will be able to classify any real number into its proper category. Our main goal is to understand the different types of real numbers and how to tell them apart. We'll start with the most basic building blocks and work our way up to the entire set of real numbers. Let's begin. Let's start at the very beginning with the numbers we use for counting. These are called natural numbers. Think about how you learned to count. You probably started with 1, then 2, then 3, and so on. That's exactly what natural numbers are, the set of positive integers starting from 1. So any positive whole number you can think of is a natural number. For example, 10 is a natural number, and so is 1 million. Now, what happens if we add one more number to this set? The number 0. When we include 0, we get a new set called whole numbers. So whole numbers are simply the natural numbers plus 0. They are the non-negative integers. This means every natural number is also a whole number. For instance, 5 is a natural number and it's also a whole number. But 0 is a whole number, but not a natural number. We've covered positive numbers and 0. But what about negative numbers? When we add the negative counterparts of the natural numbers to our set of whole numbers, we get the integers. Integers include all the whole numbers, plus all the negative whole numbers. So it's the set of all positive and negative whole numbers, including 0. This means that every natural number is an integer, and every whole number is an integer. For example, -7 is an integer, 0 is an integer, and 12 is an integer. So far, we've only dealt with numbers that don't have any fractional or decimal parts. But what about numbers like 1/2 or 3.75? This brings us to our next category. These are called rational numbers. The word rational comes from the word ratio, dankara. A rational number is any number that can be expressed as a ratio or a fraction of two integers. So a rational number is any number that can be written in the form p over q, where p and q are integers, and q is not 0. Let's look at some examples. The fraction 1/2 is rational because 1 and 2 are both integers. The fraction -3/4 is also rational. What about the integer 5? Yes, 5 is rational. We can write it as 5 over 1. In fact, every integer is a rational number because you can always write it as itself over 1. Now, let's talk about decimals. How can we tell if a decimal is rational? There are two types of decimals that are rational. First, we have terminating decimals. These are decimals that end. For example, 0.75 is a terminating decimal. We can write it as the fraction 75 over 100, which simplifies to 3/4. So 0.75 is rational. Second, we have repeating decimals. These are decimals that have a pattern of digits that repeats forever. A classic example is 1/3. When you divide 1 by 3, you get 0.3333 with the 3 repeating forever. We write this as 0.3 with a bar over the 3. This is a repeating decimal, and it is rational. Any repeating decimal can be converted into a fraction of two integers. So to recap, a number is rational if it can be written as a fraction of two integers, or if its decimal representation is either terminating or repeating. Now, what about numbers that don't fit this description? Numbers that cannot be written as a simple fraction. These are called irrational numbers. An irrational number is a number that cannot be expressed as a fraction p over q, where p and q are integers, and q is not 0. In terms of decimals, this means an irrational number has a decimal representation that is both non-terminating and non-repeating. The digits go on forever without any repeating pattern. Let's look at the most famous irrational number. It's pi, the ratio of a circle's circumference to its diameter. The digits of pi go on forever without repeating. This makes it an irrational number. Remember, the fraction 22/7 is just an approximation of pi, not its exact value. Another important irrational number is Euler's number, e. It's the base of the natural logarithm and is approximately 2.71828. Like pi, its decimal expansion is non-terminating and non-repeating. So to summarize, irrational numbers are the opposite of rational numbers. They cannot be written as a fraction, and their decimals go on forever without repeating. Now that we've defined rational and irrational numbers, we can put them together to form the set of all real numbers. The real numbers, denoted by the letter R, are simply the union of the set of rational numbers and the set of irrational numbers. This means that any number you can place on a number line is a real number. It's either rational or irrational, but it can't be both. Let's visualize this with a diagram. Think of a large rectangle representing all real numbers. Inside this rectangle, we have two large, non-overlapping circles. One circle is for rational numbers, and the other is for irrational numbers. Now, inside the rational circle, we have a smaller circle for integers. And inside the integer circle, we have an even smaller circle for whole numbers, and inside that, the smallest circle for natural numbers. This diagram shows the hierarchy. Every natural number is a whole number, every whole number is an integer, every integer is a rational number, and every rational number is a real number. Irrational numbers are also real numbers, but they are in their own separate category. Now, let's tackle a common point of confusion, numbers involving roots. How do we determine if a number like the square root of 9 is rational or irrational? The key is to simplify the root first. Let's look at our first example. Is the square root of 9 rational or irrational? To find out, we simplify the root. The square root of 9 is 3, because 3 times 3 equals 9. So the square root of 9 simplifies to 3. Now we ask ourselves, is 3 rational or irrational? We know that 3 is an integer, and all integers are rational. Therefore, the square root of 9 is a rational number. Let's try another one. Is the square root of 2 rational or irrational? We try to simplify the root. Is there a whole number that, when multiplied by itself, equals 2? Number 1 times 1 is 1, and 2 times 2 is 4. The square root of 2 is not a whole number. In fact, the square root of 2 is approximately 1.41421356. Its decimal expansion is non-terminating and non-repeating. This means the square root of 2 is an irrational number. So the rule is, if the root simplifies to a whole number, it's rational. If it doesn't, it's irrational. Let's practice this with a few more examples involving different types of roots. First, let's consider the cube root of 27. We need to find a number that, when multiplied by itself 3 times, equals 27. Let's try 3. 3 times 3 is 9, and 9 times 3 is 27. Perfect. The cube root of 27 is 3. Since 3 is an integer, and all integers are rational, the cube root of 27 is a rational number. Now for our final example. Is the square root of 12 rational or irrational? First, let's try to simplify the root. We look for perfect square factors of 12. We know that 12 is 4 times 3, and 4 is a perfect square. So we can rewrite the square root of 12 as the square root of 4 times 3. Using the properties of roots, this is the same as the square root of 4 times the square root of 3. The square root of 4 is 2, so our simplified expression is 2 times the square root of 3. Now we have a rational number, 2, multiplied by an irrational number, the square root of 3. The product of a non-zero rational number and an irrational number is always irrational. Therefore, the square root of 12 is an irrational number. The key was to simplify the root first to see its true nature. Let's quickly recap what we've learned today. We've explored the different types of real numbers. We started with the natural numbers, which are the counting numbers. Then we added 0 to get the whole numbers, including negative whole numbers gave us the integers. We then learned that rational numbers are any numbers that can be written as a fraction of 2 integers, or whose decimal is terminating or repeating. Irrational numbers are the opposite. They cannot be written as a fraction, and their decimals are non-terminating and non-repeating. Finally, we saw that the set of all real numbers is simply the combination of all rational and irrational numbers. We also learned a powerful technique for classifying numbers with roots. Simplify the root first. If it simplifies to an integer, it's rational. If it doesn't, it's irrational. You are now equipped to classify a wide variety of real numbers. Keep practicing, and you'll become an expert in no time. Thank you for watching.